Everybody, I think we can start. We're complete. Just the screen. Yeah, good morning, everyone, and a very warm welcome to this webinar on transparent, safe, and trustworthy AI, where we discuss enhancing human AI collaboration in critical infrastructure. This webinar is a part of the work package 2.3 of the AI for RealNet project, a project that is funded by the European Union's Horizons initiative. So to start with a brief introduction. So my name is Mohammed Hassouna. I'm a research assistant at the Fraunhofer IEE and the University of Kassel, and I'll give a brief introduction of the project and why we're doing the webinar today. But so first of all, also welcome to all of our fantastic speakers for today, starting with Riccardo Chavariaga from Zürcher Hochschule für angewandte Wissenschaften, Alberto Vitelli from Politecnico di Milano, René Heinrich, my colleague from Fraunhofer, and from TU Delft we have Clark Borst today, and finally Toni Reffler from the Fachhochschule für Nordwestschweiz. Also special thanks to Bianca Salva for the support for the organization of this webinar, in particular with regards to the logistics and making sure that everybody gets the invitation. So without further ado, let's start with the broad overview of the AI for RealNet project. So I think the core idea of the AI for RealNet project is to help decision-making in critical infrastructure environments, right? So when we look at real-world infrastructure networks, such as power grids, train networks, and also air traffic management cases, we have this complex infrastructure where we need help or decision support or even automated decisions by AI. And we model these environments as a so-called MVP, or a mock-up decision process, where we have an abstract representation of a state, describing the current state in the environments, and then we have a decision-making AI entity that performs specific actions on these environments. And for each action, we receive then a reward signal indicating whether that action was actually any good, right? And doing so this iteratively, we train, for instance, reinforcement learning agents to optimize certain processes and solve problems in these complex infrastructure environments. So to help us achieve all these goals, there's a lot of research needed, of course, in machine learning and in reinforcement learning in particular. We have multiple complex areas where we look at in the project, but the focus today is actually on transparent AI. Right, so we don't want just to have good decisions made by AI entities, but rather want to have also explainable policies and transparent design of these AI systems. We also look at integrating safety rules into these AI agents and to ensure trustworthiness. And we also look at how regulation affects all of this and how our methods and the developed methods and current state-of-the-art research as well is compliant with such regulation. So the objective, I would say, is to create a multidisciplinary approach where we combine AI algorithms with open source digital environments in order to design AI-based decision systems. For that, we look at 3 existing open source AI environments, digital environments of electricity networks, railway networks, and air traffic networks, named Grid2Op, Flatland, and Blue Sky. And we look at utilizing these environments as well as boosting development in these environments as well. Now, when you look at AI assistants or even AI agents, we can kind of find out 3 degrees of autonomy. So we have full human control with assistance and recommendation given by the AI, And we have it the other way around as well with fully autonomous AI. But we also have something in the middle where we have co-learning between human and AI and joint decision making. So for the project, we have identified 6 important use cases that we look at. I won't go into detail into each specific use case. We have 2 use cases per domain. And just to look at how AI agents make the decisions there, for grid to op or for the grid use case, we have full human control with assistance from the AI through recommendations of topological actions, redispatch actions, etc. And for train networks, we have fully autonomous AI, but also some component of joint decision making. And for the ATM use cases, we have mostly full human control, but also joint decision making. So regardless of the degree of autonomy there, we notice in critical infrastructure that there's always a human involved, and it has a central role in decision making, right? So therefore, we always need trustworthiness of such AI systems. A part of trustworthiness is the regulatory and safety requirements. So if we can make sure that AI agents follow safety standards and adhere to safety constraints, then we can improve this. This goes the same way for regulatory issues as well. There's also the need for explainability, meaning that we don't just want black box optimal decision in our environments, but we also want to have a way to find out how these AI agents took certain actions and justify these. And finally, we have the transparency issue where the design of the AI decision support and or decision systems has to be done with transparency in mind in order to enhance, since we have this human AI interaction, we need to enhance the understanding and the usability and also look at psychological issues such as reducing cognitive stress, for instance, and much, much more. So that's pretty much it from my introduction. Coming up, we'll have Ricardo introducing us into the topic of trustworthiness and regulatory compliance. And afterwards, Alberto will talk about safe reinforcement learning and how to integrate safety constraints into the learning process and decision process of reinforcement learning agents. Then we'll move on to explainable AI, where we look at how to make how to demystify the black box nature of AI or of reinforcement learning through explainable AI methods. And then Clark will talk to us about how to design systems for transparency. And finally, Tony will discuss the psychological side of this with the human agency, and we will finish off with a question and answers session. Having said that, I'd like to move on to or hand over to Ricardo.
Thanks, Mohammed. Can you go to the next slide, please?
Yeah, sure. You can also share your screen if you like.
Second. Can you see my screen now?
Yes.
Great. So, sorry. So thank you for joining today, and I will start by discussing the concept of trustworthiness and how this can be assessed for regulatory compliance as well as the requirements that have been identified for the system, in particular systems for critical infrastructure. And we can start by mentioning how we are at the moment where there are upcoming regulations for artificial intelligence systems that come on top of the existing regulations that we may find in the particular fields that we are working on. And a particularity of these regulatory frameworks for artificial intelligence, and in particular the AI Act for the European Union, is that it doesn't only include technical aspects, but also socio-technical aspects, such as societal and environmental well-being, accountability, diversity. So it is important when we try to assess the trustworthiness of a system and to ensure regulatory compliance, that we have a structured approach to identify what do we mean by these different dimensions, these technical and socio-technical dimensions, and link them with the specific procedures, methods, processes that can be used to verify if we are actually fulfilling the requirement. So when we are going into regulatory or conformity assessment, we need then to identify what do we mean by each of these different dimensions. And in the next talks, we will see how are we addressing some of them. And this needs to be aligned with existing standards, and we will have both AI-specific standards as well as domain-specific standards. And in certain cases, there are not yet standards being clearly established, so we need to rely on the existing practices of our specific domains or other sources for that. And these standards will provide us some guidelines on how can we address these issues. And for each of them, it is our role to identify what are the specific processes, documentation, and importantly, metrics that can indicate that we are actually addressing them in the way that we intend to. However, often when we talk about assessment, we think about an ex-post assessment, meaning that we have done a system, and then afterwards we will see whether we have reached a design that actually fulfills the needs for the regulatory requirement. However, this is not enough. So it is more and more clear that we need to identify these processes, these methods, not only for doing an assessment, but already integrate them from the early stages of the life cycle and follow them throughout. So this is actually already included in the expectations from the regulatory requirements of the AI Act that talks about risk management systems that should be established, implemented, documented, and maintained, not at a single point, but throughout the life cycle, including after the deployment of the systems. So if we want to implement that throughout, and we want to make our systems compliance by design, then it becomes increasingly important to identify both functional and non-functional requirements and KPIs that are related to the trustworthy dimensions from the early stages of development. And once they have been identified, then integrate them into the development cycle by, among other measures, adopting an appropriate risk management approach that does a continuous assessment of the impact of our design decisions into the different dimensions that are expected in the regulatory requirements. So here we have this confluence between the identification of technical and socio-technical aspects and a way to define how to develop our systems. So in order to do that, we can have different alternatives of approaches. Some of them are descriptive frameworks that may range from requirements for human-centered AI to other aspects that also include the aspects for human-machine interaction, for instance. And these frameworks are typically more technically oriented. They not always include the same socio-technical aspects that are included in the AI Act, for instance. So they serve a purpose, but may have certain limitations, in particular when we are thinking about unforeseen risks or early stages of development. In addition to that, we have other type of tools that are the risk management frameworks, and there are different examples that are coming here. Here I'm showing the NIST risk management framework or the ISO IEC standards for risk management, and in particular for AI risk management, which is being an ISO standard has also been adopted as an European standard and will be expected to be one of the basis of compliance assessment for the AI Act. So these ones allows us to manage and to track and monitor identified risks throughout the life cycle. And but they are not necessarily designed for the socio-technical aspects that are in the AI Act. So more on these socio-technical aspects, we are also saw in the last years the appearance of quantitative and qualitative assessment for these aspects that can complement the other approaches that I showed before. So in general, the core message is that for regulatory compliance in aspects of trustworthiness, it is important to include that from the very beginning by identifying requirements and then track them throughout. And these three types of tools can help the developers in doing it so. And just very briefly, this is one example of one of the initiatives that we have taken in AI for RealNet. We have taken this assessment list from Trustworthy AI that followed the EU framework for Trustworthy AI that decomposes these different dimensions into specific sub-areas. And we have used this framework to define and to refine the use cases for AI for RealNet that Mohammed mentioned before. So what we have done here is to look at the initial definition of the use cases to identify whether they were addressing the requirements that were comprised in this assessment list. And for those aspects that were not already included and were relevant for the use cases, then we ensure that there were requirements that were explicitly addressing them. And for sake of time, I'm not going to enter into details, but you can see the outcome of this process in the description of the use cases that is available in the project website. So to close, one of the elements is to include these requirements, technical and socio-technical, from the very beginning. There is a need for improved tools to do this assessment throughout the life cycle and to integrate them with the risk management models. And these are part of the work in progress that we are developing in the project, and we'll be very happy to share these outcomes in a future occasion. And then I will stop here and thank you for your attention so far and leave the floor for the next speaker. Thank you.
Okay, I think it's my turn. Let's see if I can share my screen. Okay, do you see my screen? Okay, yes. Perfect. So good morning, everybody. I'm Alberto Metelli. I'll be presenting this part on safe reinforcement learning. So first of all, let's start revising the definition of reinforcement learning. So reinforcement learning is a class of approaches that deal with sequential decision-making problems which are characterized by an uncertainty on the environment. So we don't know the environment in which our agent will be acting. The goal in a reinforcement learning problem is to find what is called the policy, that is a way of performing actions on the environment in order to maximize a certain utility function, which is typically represented in reinforcement learning as the expected return, that is the discounted sum of the rewards that our agent will collect by interacting with the environment. By maximizing this utility function, our agent will accomplish a certain task, which is defined by means of this notion of reward that the agent gets at every time step. So this is the general definition of reinforcement learning, which is based on the idea of expectation. So we would like to find the policy which maximizes this expected sum of rewards. However, in many real-world scenarios, we might be interested in focusing on different utility functions because we might have some constraints which come from the specific application scenario, like the ones we deal with in AI for RealNet, that are characterized by having some safety constraints that need to be satisfied. So typically in the reinforcement learning literature, we distinguish between two different notions of safety. which essentially depend on whether the safety has to be enforced on the final behavior that the agent delivers at the end of the learning process, or if the safety has to be enforced during the learning process. So in the first case, so when safety is required at the end of the learning process, we don't actually care on the behavior that the agent demonstrates during the learning process, which might violate safety, while in the second case, when the safety has to be enforced throughout the learning process, instead, we have more demanding constraints, and this may limit the exploration of the environment because some behavior need to be prevented because they are not safety. For the rest of my presentation, I will discuss some formulations of these two notions of safety. So let's start from the first one. So when we would like to ensure safety at the end of the learning process, the typical approach consists in changing the optimization criterion. So we are no longer interested in maximizing the expected sum of the rewards, but we change that objective function. And now I will comment basically three possibilities for this that are robust reinforcement learning, risk-sensitive reinforcement learning, and constrained reinforcement learning. In the case of robust reinforcement learning, the notion of safety is strictly related to the fact that we have uncertainty on the environment parameters. Namely, we don't know which environment the agent will be required to face. And this is typically formalized by a notion of uncertainty set. So we don't know which the environment will be, and we have some ideas on in which set this environment will belong to. So the idea at the basis of robust reinforcement learning is to maximize what is called the worst case expected return, which is the expected return, as we commented before, but calculated in the most challenging environment among the ones that are plausible to be encountered by the agent. This formulation, as you can see in mathematical terms in the right part of the slide, can be formulated as a min-max game, where the min stands for the fact that we don't know which will be the environment that the agent has to face. There are efficient solutions for this problem for particular classes of uncertainty sets like rectangular ones. The second possibility that we have for safety reinforcement learning is risk-sensitive RL. Here, the notion of safety instead is more related on the stochasticity of the environment. That is, we want to maximize, we want to guarantee a certain gain in terms of expected reward under a certain probability, which is typical, for instance, in financial scenarios. Again, the approach that is adopted in reinforcement learning for dealing with this scenario is to change the optimization criterion by focusing on what is called a risk-sensitive transformation of the expected return, that are basically transformation of our objective function which penalize for behavior which are characterized by a high stochasticity, so a high variance. Here I have listed some, say, standard possibilities, which are the mean variance, the conditional value at risk, and the volatility. The last possibility when we want to enforce safety at the end of the learning process is constrained reinforcement learning. Here we explicitly model safety by means of a constraint in the optimization sense. So we would like to maximize the expected return as well, but formulate it as a constrained optimization problem, which involves the presence of some constraints. There is a full theory for this, which is based on the notion of constrained Markov decision processes, and from an algorithmic perspective, the approach is the typical approach which is used is the one based on Lagrangian multipliers, in which we solve the optimization problem by turning it into a min-max unconstrained optimization. Finally, the last view of safety that I have mentioned at the beginning is the notion of safety during the learning process. So the case in which we are interested basically in ensuring that safety is guaranteed throughout the learning process. And here I have listed two possibilities for this. One is called safety exploration, which is characterized by enforcing the fact that during the learning process, the performance demonstrated by the agent must remain above a certain threshold, which is given by the user. So there is a baseline behavior, and we want that our agent behaves better, at least for a reasonable amount of steps compared to that baseline. Of course, the more we want to be close to the baseline, the less we are allowed to explore the environment, and therefore we may not reach the best performance, so the global optimum of our learning problem. The second possibility that we have for ensuring safety during the learning process is monotonic performance improvement. Here, instead, we are not focusing on a performance threshold. Instead, we would like to guarantee that the performance on successive learning steps of our algorithm is guaranteed not to decrease, at least with a certain probability. This will lead to a slower learning process, but which typically displays smoother behavior. And with this, I think I finished. Thank you. I leave the floor to the next speaker.
Yeah, thank you very much. I'm gonna try to share my slides as well. Okay, I hope you can see my slides now.
Yes.
Okay, thank you very much for the feedback. Yeah, so hi everyone. My name is René Heinrich. I'm a researcher at the Fraunhofer IEE, and I would like to give you now a short introduction to Explainable AI. Okay, no. So as many of you might know, many machine learning models, especially deep learning models, are black boxes. So it's very hard for us as humans to understand how these models make their predictions and what concepts they have learned. And here the field of explainable AI comes in and tries to address this issue by providing us with methods to gain a better understanding of such black box models. There exist many different explanation methods, but they can roughly be categorized in two big categories. The first category are post hoc explanation methods. This is the category where most of the research focuses on currently. Such post hoc explanation methods are methods that try to explain black box models that already have been trained. So these are like external separated methods that we can use to analyze black box models. Whereas the second category, inherently interpretable models, here we try to design the model architecture of a model from the beginning in such a way that it is inherently interpretable and understandable to us as humans. We can provide explanations of different scopes. Usually we distinguish between local and global explanations. Local explanations are explanations that aim to provide insights into individual predictions of a model. For example, if you have an image classification model, like here on the bottom left, that classifies this individual image of a bird correctly as a bird, local explanations can help us to understand on which areas in this image the model focused to make its classification. Global explanations, on the other hand, do not provide explanations for individual predictions, but they try to explain the entire model behavior. So global explanations help us to gain insights, what concepts the model did learn in general, and what patterns it uses to make classifications for certain classes. We can provide explanations in different formats, such as summary statistics. Most often we use visualizations to provide explanations. However, you can also provide them in the form of text or in the form of example data points. And when we generate explanations, it's always important to have our target group in mind, since there might be many different target groups for the explanations of our models, such as data scientists, machine learning engineers, domain experts, managers and executives, users affected by the model, or even regulatory authorities who have to audit our models. And since all these different target groups have a different background knowledge of AI and also of the domain where we apply our model, they have different needs and requirements on the explanations. So it's very important that we always customize and optimize the explanations to the needs of our target group. One of the most popular post-hoc explanation methods is SHAP, Shapley additive explanations, which is a method to approximate Shapley values from game theory. SHAP calculates how each feature contributes to a prediction of a model and thus provides us with a kind of feature importance values. It provides local explanations. However, by aggregating the local explanations of multiple samples, we can also use SHAP to get global explanations. And the nice thing about SHAP is that it has a very sound mathematical foundation. For example, it has been proven that SHAP unifies many other post-hoc explanation methods such as LIME, LRP, or deep lift. Like I said, SHAP approximates Shapley values from game theory. What are Shapley values? They were originally proposed as a method to distribute the gains of a cooperative game fairly among a group of players. And we can also apply this to explainable AI by defining the gain of a cooperative game as the prediction of the model, and by defining the group of players as our set of input features. And thus we can use Shapley values to calculate how much each feature contributed to the prediction of a model. However, if we want to calculate the Shapley values exactly, we have to train a separate model for each combination of a subset of the input features, and this gets computationally very expensive if we have a lot of features. So here SHAP is a very nice approach to approximate these Shapley values quite fast. And besides its solid mathematical foundation, it's also applicable to various data types such as tabular data, image data, and so on. And it's also model agnostic, meaning we can apply it to arbitrary machine learning models. However, there is this quite famous paper from Cynthia Rudin from the year 2019, which showed several drawbacks of post-hoc explanation methods. Specifically, post-hoc explanation methods are often prone to approximation errors, meaning the provided explanations do often not fully match the model's calculations, which makes it quite hard to trust these explanations. And sometimes the explanations can even be misleading. And moreover, they also argue in the paper that black box models and thus also post-hoc explanation methods are often unnecessary because in most cases we can find an inherently interpretable model that achieves a comparable accuracy or performance to black box models and at the same time provides us with reliable explanations. Such inherently interpretable models can be like quite simple traditional machine learning models like linear regression or decision trees. However, when we deal with unstructured data like audio, images, graphs, and so on, such traditional machine learning models usually perform much worse than deep learning models. So the challenge here is to develop inherently interpretable deep learning models. And there's one quite famous approach from Chen et al. From the year 2019, the deep prototype learning for image classification, which uses deep learning only for feature extraction, but bases its prediction itself on an inherently interpretable classifier. And this model learns several prototypes for each class, which represent characteristic parts of training images for each class, and the model makes its predictions for new test images by comparing all patches of a test image to all the prototypes that the model has learned, and then classifies the image as the class to whose prototypes it has the highest similarities. And using these prototypes, we get explanations for the model's decision automatically. The authors of the paper have shown that the explanations provided by the deep prototype learning model are similar to the explanations that domain experts would give for image classification. And they did also show that the model achieves a performance that is comparable to other black box deep learning models for image classification. With regard to our application of power grid operations, explainable AI can also be very interesting. For example, if we have a reinforcement learning agent that provides us with actions on the power grid, for example, if we have overflows and the reinforcement learning agent tries to solve them, then explainable AI can help us to figure out which features or which parts of the power grid the reinforcement learning agent considered important to make its decisions, since power grids naturally form a graph structure. Applying and adjusting explainable AI methods to graph neural network-based agents is needed and an interesting future work. And since power grids are critical infrastructure, we also require reliable explanations. So here, adjusting approaches like the prototype learning model to power grid operations could also be a very interesting future work. So to summarize, currently most research in the area of explainable focuses on post-hoc explanation methods. However, these methods have several drawbacks and the explanations might be too unreliable for high-risk AI applications. So here we urgently need more research on interpretable deep learning models. Yeah. Thank you very much so far from my side, and then I would like to give the floor to the next speaker.
I am the next speaker. So can you see my screen?
Yes, thank you.
So I'm going to talk about a little bit about designing for transparency. So you've also already heard some things about explainability and also interpretability. And they also mainly focus on the model side of things, like getting a little bit more insight into the model and how the entire architecture works. There's also a side of transparency which might be useful more also for operators who are not trained to understand these kind of mathematical models. So another thing for, especially also for operators, some kind of an operational transparency, something that we have also been dealing with in the aviation domain, is that when we think that more tasks are being automated, then we also think that there's like an incorrect belief that then the role of the human will become less. But in safety critical operations, actually, we put the human in charge to basically bear the final or responsibility of the safety of operations. So that means that when we going to automate more, also the role of the human operator becomes, well, more important and also more critical, but at the same time also more difficult, because they have to deal with automation and trying to understand it. So a good example of like a lack of transparency for operators is also demonstrated by the Boeing 737 MAX accident, or well, I would say the two accidents. That was a lack of well, automation transparency, because the pilots did not know that there was a system that was actually failing, and that was a very critical system to maintain the safety of the aircraft, to keep it well, sort of airborne. Of course, there were many things at play here. Also, a lack of transparency from like corporate decisions, but eventually it trickled down also to the pilots, where they did not know that there was well, this kind of a system that was basically ignoring or be very counterproductive in terms of yeah, their steering actions. So in terms of the transparency, I think, yeah, we've also gone a little bit over that in the previous presentations. So we have a black box automation. You also have, in terms of transparency, I think that's mostly the transparency that ICT experts consider. There's the so-called seeing through transparency, that the system that you have is so perfect and so, for example, intuitive, that for the user, it doesn't even know that they are being supported by automation. Of course, that's also what the engineers try to achieve at Boeing with that MCAS system. But of course, yeah, they failed, yeah, because the system was actually capable of failing. So they try to achieve seeing through transparency, but in the end, yeah, that completely backfired. So we are more or less looking into, yeah, seeing into transparency, such that we can sort of more like open the black box and see inside the black box, turn it into a glass box, and really see like, yeah, what are the automation's responsibilities, the goals, inner workings perhaps, and also, yeah, its performance. So for the operator, transparency is, well, I think the most important communication means for the automation to provide more feedback to the operator is by means of the human-machine interface. So the human-machine interface is often seen as a very critical and crucial element to close or successfully and safely close a manual, but also a supervisory control loop. So Erik Rolnakel, a professor from Denmark, once said like that the goal of the interface is to provide the right information in the right way and also at the right time. That seems like a very logical and plausible explanation, but of course it is rather meaningless if we don't know exactly what right is. And also, how can we find right? So what is the right information? What is the right content? And when is the right time to show things? So, and therefore you also have like different approaches to find right. So for a long time, approaches to find right has been mainly dealing with looking at, well, the capabilities, the goals and the skills of the human to reflect that in the content, structure and form of the interface. Or we look at the automation, the black box, looking at the algorithms, the processes and the logic, for example, like the explainability models, and try to, well, squeeze that onto the content, structure and form of an interface. But what is often forgotten is that, yeah, both a human operator and a machine, they all work in the same work domain. So the work domain more or less provides the context in which actions can take place. So in other words, the work domain, well, if we talk about physical systems, basically the laws of physics and the dynamics, they basically define like an operational envelope. Like the safe states a system can be in. And of course, it doesn't matter whether you are a human operator or like a computer operator. Yeah, you all have to respect or stay within the safe operational envelope. So so including this work domain is also a very important thing thing to consider. So, well, also in theory and practice, there have been different ways on how to design an interface. So if you focus more on the human side, you tend to adhere to user-centered interface design approaches. If you focus more on the machine, you focus more on like model-centered approaches, which can be like a reward decomposition, showing search trees and stuff like that. And in between, you will have like more like the ecology-centered approaches, which try to, well, capture or model the operational envelope of a system, and then try to portray these operational envelopes, well, on an interface, and also embed these operational envelopes in the machine, such that the machine is also aware about the constraints imposed by the laws of physics. So if you would translate that, yeah, so you can also try to combine everything, where we are, yeah, when we focus more on the needs of the human, you can define perhaps like operational transparency, because an operational user is not really interested always in the very dirty ins and outs of what is happening inside the machine. So they just want to know, is the action proposed by the machine, is it safe? And what kind of operational impact will it have? Yeah, what is the well, expected efficiency of the solution that is being proposed? And what other solutions might there be? And in terms of, yeah, if the human wants to dive deeper, they might want to know a little bit more about, okay, what is the operational envelope? So is the solution proposed by the automation, does it fit within the space of possibilities? And what other possibilities were they and have perhaps also been explored? And then finally, if you really want to dive deeper, you can perhaps also look at, yeah, what individual yeah, sort of decisions and trade-offs have been made by the machine in order to finalize or to conclude itself to, well, only converge to one particular solution. So in terms of operational transparency, so there's also a little bit the debate about the explainability and interpretability. That was also mentioned by René. But indeed, if you are a human operator, you are more like interested in, well, the intentions of the machine. What does it try to do and how does it try to help you? You want to know, like, is the solution, is that feasible? And also what kind of impact will the solution have? And that's important for a human operator to sort of make a trade-off, and whether you decide, yeah, so what kind of waypoints did it introduce, and what are the settings of those waypoints? But they also can go, well, I'd say further down, like what is the operational impact? Yeah, so what is basically the closest point of approach with another vehicle, and why did it, for example, not consider to fly more direct to that point? Yeah, that's because that point is not basically safe. So therefore it considered another route. But they can also look at, like, okay, so what kind of information did the machine consider in coming up with the solution? And is the solution within the capabilities, the physical capabilities of the drone? So in this case, yeah, the AI also considered the different wind conditions in order to plan the route, and also considered basically the range endurance of that drone based on its battery capacity. And finally, yeah, we also added a way for humans to inspect basically the whole decision process of the machine. So basically step through all the points in its planning process to visualize search trees, but also allow that to be sort of interactive, such that the human operator can really explore how the AI came up with a particular decision. And this is one in particular, it's a grid-based pathfinding algorithm. But if you would change it to another type of algorithm, like a more sampling-based algorithm, so then you can also see that the decision in the same situation is different. But also by inspecting the search trees, you can see that indeed, the AI generated its path using very different way of looking at or modeling the state space of the system. And so instead of regular grids, it was now looking at a sort of random sampling points to find the root. So to close this off is that, of course, transparency might seem a good thing because it can build trust and understanding. But of course, as you have seen from the previous animations, is that you might also open Pandora's box. So it's really about finding a good trade-off between workload and usability. And so if you open the black box too much and confront the human operator with too much detail, there might be it will increase the workload in order to step through all of these different layers of information and try to make sense of it. And that will also delay responses. But of course, if you then reduce the transparency, then you might make it a little bit more workable and usable for the human operator. But then you might also lose some understanding and also supervisory control performance. And you also make it more difficult for the humans to understand when it is perhaps not good to rely or implement a particular decision. So I think that is so far what I have. So I would likely hand it over to Tony.
Thank you, Clark.
Can you share your screen, I guess?
So can you see my slides now?
No, not yet.
No, not yet.
I don't know why it doesn't work.
Maybe I can share them and just move on with the slides, if that's fine with you.
The moment, maybe. I don't know. Yeah. Can you share my slide?
Yes.
I don't see them now.
Oh, okay.
Okay, good. Thank you. So my name is Tony Webster. I'm representing the School of Applied Psychology of University of Applied Science and Arts Northwestern Switzerland. And as a psychologist, I now put the psychological perspective on the topic. Maybe you can go to the next slide. So I'm talking about human agency, and I think it's important to say when we're talking about AI, human collaboration in our projects, we are focusing operative decision making in network control, and we are looking at the highly experienced human experts who have to take decisions that might be risky or where the stakes are high. I think it's important to say so because human AI collaboration for consumers, for example, would be something totally different. And whatever I tell now focuses on these human experts. And human agency, I took the definition out of the European Commission's guidelines. Human agency aims at supporting individuals with AI in order to make them better in whatever task they have to perform, taking decisions with high stakes. That's what we are focusing in our project. Can you go to the next slide? So here we have some problems that we know for a long time in human machine collaboration, and Clark was also mentioning some of them. So one of them is that very often when we automate tasks, we put the human into a situation where the human has to take a role which exceeds their capabilities. And in AI, that's also a problem because the AI, when solving a problem and making a recommendation to the human, the AI takes much more information into consideration than the human is capable to, and processes the information also much quicker than the human can process information. But still, we expect the human to judge whether the recommendation from the AI is a good one, to supervise the AI, and that's a kind of an impossible role the human often gets. Clark was mentioning supervisory control. That's actually the problem that I'm discussing here. And a second problem is that from a psychological point of view, we see very often that as soon as we give the human tools, semi or fully automated tools that are expected to support a human, humans start to over-rely on that. So we have this automation complacency where humans over-rely on the automatic tools, and that leads to typical errors like omission error and commission error. Commission error is when the tool tells the human to do something and it's the wrong thing, but the human doesn't realize. And omission error is when the human expects the tool to make the human alert of something, but the tool doesn't do so, and then the human is not reacting also they should. And these problems are well known, as you see from the dates of the publications for a long time. And both problems may even worsen with AI, because the AI, as we heard, black box, very difficult to understand for the human, makes these problems even worse. So you can go to the next slide, Mohammed. Now, we heard some talks from René, from Clark, about explainability and interpretability and transparency. And that's very important, what we heard there, but still there are some problems with that. And that's why in our research, we try to go beyond this providing comprehensibility by explainability or interpretability. And why is that so? There are some research in human AI interaction, for example, from Buchincha, that realized that humans, when they work with an AI and get explainability or explanations, they don't really engage with these explanations. They don't really consider the explanations. So Buchincha found in our research that when human AI combination needs to solve a problem, then humans over-rely on the recommendation they get from the AI and accept better recommendations that they would, how to say that? So if they do work without the AI, they make better decisions in that experiment than when they work together with the AI. So that means that the humans over-rely often on the AI, and then there is some approaches that they call cognitive forcing. The cognitive forcing means because the human over-relies on the AI and doesn't engage with the explanation, we want to force him to engage with the explanation. For example, by delaying the recommendation that comes from the AI, or by asking the human for a decision before the AI gives the decision to the human. But still there, this cognitive forcing doesn't really work. So the main problem is that humans often are not really taking into consideration the explanation they get from the AI. And that's why we try to find another way of supporting the human by the AI. And you can go to the next slide, Mohammed. Yes. So what I try to explain right now is that this recommendation-based AI, the human gets a recommendation and a sophisticated explanation, but humans still over-rely on that. And it's very important, I must say, that we do more research in this domain, as we heard from Clark and from René. But we try also to go into another direction that I want to show with the next picture, Mohammed. Yes, the idea would be to really have an AI that augments human capabilities. And the picture for that, I think, is the bicycle is very well, because the bicycle is a tool that really augments the human power. So a bicycle has no engine at all, and it only uses the human's power to drive around, and the bicycle augments the human power in a way that with the human own power, the human can drive quicker and have more mobility than without the bicycle. And if we even add an engine to an e-bike, then it augments the human power even more. And that's something we also are looking for with the AI. So how can we design the AI so that the cognitive power of the human is not replaced or exceeded, but rather augmented. And you can go to the next slide, and that will be my last slide for today. The main idea is that we have an AI that explicitly supports human cognitive processes in different domains, for example, in decision making. You know, if you analyze how human experts, like, for example, air traffic controllers, take decisions, then that's a very complex cognitive process. They need to monitor the situation, they need to update permanently their situation awareness, their mental models about the actual situation. They need to build up a lot of knowledge about where are the leverage points, which are the different points that they need to have to keep in their eye. And all these processes might be supported by the AI. For example, supporting human decision making regarding managing the attention. So the AI would, like a bicycle, support the human expert in managing their attention to see the right developments or the important developments in the environment. And for example, also could support the AI, the human, in taking a decision by providing the human with information about different effects of different options they have to decide. That would be supporting human decision making. But we can also support human learning as a cognitive process. For example, the experts, they need to build expertise on the environment or the network they try to keep under control. For example, which are the leverage points? So the humans have a lot of knowledge about that, and they also have assumptions about that. And the AI could, for example, support them in learning even more about the environment and the leverage points. There is a concept from Miller who calls it evaluative AI, and an evaluative AI is an AI where the human formulates a hypothesis, for example, about a leverage point in the environment, and then the AI goes into the data and looks for evidence for or against the assumptions the human has, and that might help the human to learn more about the situation. Also, it might support learning about weak signals. So if you want to have the human in a situation where they proactively prevent problems before they occur, they need to learn which are the weak signals they have to look for in order to see that the problem emerges. And the knowledge about that also can be supported, or the learning about that could also be supported by AI. And finally, even motivation, very important. You know, motivation from a psychological point of view also is a cognitive process. There are some cognitive aspects that must be fulfilled in order for the human to be motivated to do their work. And one of these aspects is that the humans need to experience meaningfulness of what happens in the environment they want to control, but also in the AI they use to control the environment. And the AI can, for example, help the human to understand causal relations in the environment so that the environment's behavior and the pattern they see there in the behavior become more meaningful for the human. So that's actually my last slide. Just to sum up, what we aim up is that we have an AI that is not providing the human with recommendations and putting the human in a situation where they have to judge on these recommendations and take the responsibility because they do not maybe understand the recommendations, even if it comes with explainability. Shifting more an AI that is supportive in terms of it explicitly supports human cognitive processes. Thank you, Mohammed. That's my talk.
Yeah, I think that wraps it up. Thank you very much.